Essentially, I'm going to be looking at some of the major characteristics of the systems when I started working in this industry in the mid-70s, and contrasting that to what I think are very important characteristics of today's systems and systems into the future. To summarize in one sentence, the systems back in the mid-70s, the origins of the first PLCs and the first DCS systems, at the end of the day, they really didn't do very much. Essentially, the mission was to replace the panel board instrumentation, to provide to the plant operator a view of the control loops, say with bar graphs of measurement, set point, and output for their PID controllers, to be able to engineer the control blocks within the system. And if we think about that and turn our minds back to some of the engineering processes and data collection processes of those times, you can probably all remember some of the early PLC protocols or programming where, in order to locate a data variable, such as the level of a tank in the process, you might have to indicate a table, or maybe it was a tank alarm. Boolean table number 7, the 8th word in the table, and I want to look at the 14th bit. That was the state of the art back in the middle 70s. So if we think about what's dramatically different, I have a couple key points here. First, a lot of the focus has now moved up a layer. Beyond just focusing on the real-time control of the plant, businesses are focusing on how can I achieve some economic value and how can I better integrate this into my enterprise. You know, back in the old days, the operator sat in front of a vat and maybe they had to get out a paddle and actually stir that vat. So the original automation was focused on how do we replace the operator. And now the focus is on how do we get business value. You can think of that even as a closed-loop control problem. How do I measure the value that the automation is delivering? How do I consider what the business inputs to that need to be? And how do I act in real time upon those in an environment where I have to be holistic and agile and be focused on very real-time decision-making? So a lot of the speakers during this conference have focused on this economic incentive, the economic challenges that they face. People and the safety of those people and protection of the environment serve as constraints that they have to live within. Very important that that be part of the focus. But at the same time, achieving the economic focus of things like minimizing energy costs, material costs, and maximizing the value of production and doing that in real time. So I maintain that one of the biggest differences between that old system 30 plus years ago and today's system is you look at the top layer and see how much proliferation there is in various applications, whether they be focusing on asset performance management, focusing on simulation capability to plan your plant, or do real-time simulations to predict maybe your energy usage and to react based on that simulation, how I might take and make energy decisions, or dashboards or workflow designs or batch processes. It's a dramatically different system of today and into the future than it was in the past. Not only that, even the lower layer has changed. The devices have become intelligent, and the number of control platforms, whether they be DCS or safety systems or I/O systems or SCADA systems, has proliferated as well. So we have two basic kinds of needs driving the future systems. If we look at North America, for example, most of the world out there is brownfield plants. For 30 years, people have been installing DCS systems. And what we see in most of those plant sites, of course, is a multitude of different DCS systems. So the challenge becomes, how do you integrate the data from all of those different systems? Because users want common access to every unit in their plant. On the other hand, if we look at what's happening in greenfield opportunities in the developing countries, in China, in Brazil, in India, etc., we see some mammoth projects. These are a couple examples. Reliance was one that Dave Wall mentioned. They built an initial refinery in 1998 that processed 660,000 barrels per day of crude. And about 5 years ago, they embarked on a journey to build an export refinery, which virtually doubled their capacity with an additional 580,000 barrels per day of crude and 900,000 tons per year of polypropylene. Or in Brazil, the Arnest refinery, 200,000 barrels per day. Or in Saudi Arabia, the Jubal export refinery, 400,000 barrels per day. So we're talking plants that might have 100,000, 200,000 I/O points in some of these plants. So the fundamental premise is that compared to communicating via location, for some years now, most systems, and I project into the future, systems are going to need to have object orientation in terms of their communication infrastructure. It will help merge all the data from the disparate systems in the brownfield plants where they come together with a common view of this is the crude unit, or this is the paper machine, and here's my tank level, or here's my flow measurement. The object orientation is vital to being able to exchange information among that proliferation of applications. It's also vital when you think about it for the large sites, because it becomes an unimaginable burden to try to keep track of a register location of every single piece of data in a plant. And it's very tedious to engineer that way, and I, for one, would not want to be upgrading a plant and changing to a newer release of software or something where I had to worry, do I have to pay attention to these locations? What if the controller now has a bigger memory and it has more locations? How does everything get reshuffled? So one of the beauties of object orientation is that tank level measurement is always called tank 101 level measurement. It never changes. Another thing that is a big advantage is the hierarchical structuring that's possible. So we always think as humans in a contained relationship. I'm in this process unit. I'm within this vessel within this process unit, and I want this variable within that loop, let's say. And I might want to look at maybe the measurement or the set point within that control loop. So object orientation in your communications can naturally lend itself to that human-like hierarchy that makes it much easier to organize and deal with a large number of variables. In fact, as the litmus test, on the left-hand side, I talk about object-oriented communications. Essentially, if you look at both the messaging and the engineering process, you will see that internal to the messaging, there's some communication where the receiving entity and the generating entity of that data are communicating according to the name of the object, not according to its location. And this means for the user that you're not browsing and mapping, that you don't have to say Boolean 7 word 5 ends up matching up and mapping to something called the high flow alarm in the tank. On the other hand, the mapped communications tend to always have some underlying element of registers, locations, and they always impose upon the user a process to actually map their user-friendly name to the location-dependent name. I'll go through this very quickly. We can have questions on this, but one of the concerns always is everything fast enough? And to me, the only measure is, can the data be delivered quickly enough for how that data is being used? And that will vary depending upon what layer you are within a system. But the basic answer is yes, object-oriented systems can deliver data for very real-time needs at various layers within the system. Object orientation might not necessarily be used within a pressure transmitter, where you might have a sensor that says I can measure the pressure on the sensor, but then have to turn it into a flow variable right within that transmitter. That's usually command-based or location-based. Dave mentioned Reliance, a picture of the plant. It had 30 major process units. Here's a picture of one of the control rooms and some examples of the station count to give you an idea of the size. It had 166 operator stations and nearly 100 engineering stations, 470 pairs roughly of control processors, almost 4,000 foundation fieldbus segments. It had an ESD, 32 nodes of ESD systems with 8,000 I/O points and almost 12,000 points in their fire and gas system, machine monitoring systems, PLC systems with over 55,000 I/O points. And they wanted an object-oriented infrastructure. In some of the vendors that they looked at, they would have been purchasing 30 separate systems for that plant. And with an object-oriented system, they wanted one namespace effectively for every single point in their plant, and all the systems being able to collaborate with one another. And that is possible with an object-oriented system. Picture of their control rooms where they focused on collaboration and sharing information. And they were using foundation fieldbus. So foundation fieldbus per se is not object-oriented as it communicates to the devices, but essentially the data becomes turned into an object as soon as it arrives at the touch point in the system, which is the I/O interface capability. So in conclusion, modern control systems of today, we've seen a major trend. All the systems were location-based back 20, 30 years ago. The vast majority of systems today are object-oriented in their naming and communication infrastructure, and I expect that to continue. It's suitable for a large system, it's suitable for small systems, and the real-time nature can be handled by object orientation. And a lot of benefits in terms of user costs and upgrades, etc. So thank you very much. Look forward to the panel discussion.